Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. This is the 14th lecture of numerical analysis. Today I will be talking about the Richardson extrapolation. As I discussed before, in case of the interpolation, that if we having certain data points and we want to find out approximate value of the function at a point which lies between 1 and 1.4. Then this procedure is called the interpolation. But if my interest lies, for example, I replace the data between 1 and 1.4 in got some curve, and I want to extend that curve and want to approximate value of the function at a point, for example, x is equal to -3. X is equal to 2.5. Means that which lies outside the region from 1 to x is equal to 1 to x is equal to 1.4. Then this procedure is called the extrapolation. Now, in today's topic, which is about the Richardson extrapolation, we want to approximate value of an unknown. For example, the unknown is m. We want to approximate value of this unknown using a formula, and let's assume the formula is given by n of h, where h is the step size. Whenever you are having certain data, we are having the step size, so it's as usual as we were doing before. But remember, our focus will be on n of h. N of h is basically the formula. For example, if you are going differentiation, this n of h will be any formula for numerical differentiation which you did before. If you are going some integration, so n of h will be formula for integration. Definitely the formulas of integration we will be doing after the differentiation, or something else. Any other kind of approximation, not necessary that it will be restrict to the derivative or integration only. It can be any other kind of approximation. Let's assume we want to find out a value of approximate value of this m using this formula. So of course you can see that this is the error term. And I can say that this error term is of order h raised to the power 1. The idea of Richardson extrapolation. Approximating m by using a formula n of h, and this is the error term. But you can see now that the power of h is increasing by 1 in this particular case. So I can say that m is equal to n of h plus order of h raised to the power 1. The error is starting from here. What Richardson is doing, replacing h which appears in equation number 1 by h by 2. So what will happen? The form will transform to this h will replace by h by 2. This h will replace by h by 2. When h replaced by 2, h by 2, so h square will replace by h square by 4. Similarly, h cube, so this will become h divided by 2 whole cube, which is h cube divided by 8. Similarly, h divided by 2 raised to the power 4, and that will become h raised to the power 4 divided by 16. You saw in equation number 1 that error was of order h raised to the power 1. Now the target is to find out an approximation where the order of the error is h raised to the power 2. Error is of h square. So what we will do, the target will be to eliminate this h from these two equations. Just as previously, you know this kind of procedure that's starting from your matriculation or starting from 8th or 7th. Multiply equation number 2 by 2. So this will become k1h, and you can do the subtraction, so this will cancel out. So what we are doing, because target is the cancellation of this term, so multiply second equation by 2, and subtract the first equation from here. So what will happen, this will become 2m minus m, and 2m minus m will be equal to m. Similarly, this will be 2n of h divided by 2 minus n of h. Remember, I replaced n by n1. The reason is that I will like to have a generalized form. So I started from 1. It is straightforward. 2m minus m is m. 2n of h divided by 2 minus n of h. But remember, I replaced n of h by n1 of h. This is just the matter of notation. If you multiply this by 2, so 2 and 2 will cancel. A k1h will cancel with k1 of h. Similarly, if you multiply this with 2, so this will become k2 into h divided by 2. This is k2h square. So if I take k2h square common, so this will become 1 divided by 2 minus 1, which is minus 1 divided by 2, which you can see over here. Similarly, if you multiply this with 2, so this will become h cube divided by 4. So k3h cube is common. So you will have 1 divided by 4 minus 1, which is minus 3 divided by 4, which you can see over here. And similarly, if you multiply this with 2, this will become k4h4 divided by 8. So 1 over 8 minus 1 is minus 7 divided by 8, and so on. Now let me say that, let's assume this term, I represent this by n2 of h. Then the form of the formula will be, I have rewritten this equation with replacement of this term by n2 of h. So this will be n2 of h minus k2h square minus 3 divided by 4 k3h cube minus 7 divided by 8 k4h4, and so on. So the same equation. Now further, now the target is to get error of order h raised to the power 3. Means that let's get rid of this term. When we get rid of this term, so the error will be starting from h raised to the power 3. So follow the same criteria, replace h by 2. When you replace h by 2, so m will remain as such, n2 of h divided by 2 minus k2 h divided by 2 square is h square divided by 4. 4 multiplied by 2 is 8. Minus 3 divided by 4 k3, this will be h divided by 2 whole cube, means that this will be h cube divided by 8. 8 multiplied by 4 is 32. So minus 3 k3 h cube divided by 32, that's the term we are getting. Similarly, if you replace h by 2, so this will be h by 2 raised to the power 4, which will be h raised to the power 4 divided by 16, and 16 multiplied by 8 is 128. So minus 7 divided by 128 k4 h cube, and similarly the rest of the terms. The target is to get error of order h raised to the power 3. So let's eliminate this term. So what we have to do, multiply the equation number 4 by 4 and subtract equation number 3. Multiply equation 4 by 4 and subtract equation number 3 we are getting. So this will be 4m minus m, which is equal to 3m. This will be 4 n2 of h divided by 2 minus n2 of h. And this will be, you have multiplied this with 4, so this become k2h square divided by 2, and when you do the subtraction, these two terms will cancel out. And if you come to this one, you have multiplied this with 4, so this will become 3 divided by 8. k3h cube minus 3 divided by 8 k cube h cube. And I'm doing subtraction, so this will become plus 3 divided by 4 k cube h cube. And when you do the simplification, you are getting plus 3 divided by 8, and k cube h cube is already common. Similarly, you have multiplied this with 4 and do the subtraction. So your term will be 21 divided by 32 k4 h4. And this is positive sign, and so on. The target is the approximation of m. So let's divide throughout by 3. I have replaced this term by n3 of h. n3 of h divided by 3. When you divide this by 3, so this will become 1 divided by 8k3 h cube. And this will become 7 divided by 32 k4 h cube, because you have divided both sides by 3. So you saw I replaced n by n1 of h, this term by n2 of h, and this term by n3 of h. Replaced n by n1 of h. This term, I have split this term into n1 of h divided by 2 plus n1 of h divided by 2, which you can see over there, minus n1 of h. Since the coefficient of m is 1, so I did the division by 1. Doesn't matter. It doesn't create any problem. And similarly, if I come to this term, n3 of h is equal to, can I write this is 3n2 of h by 2 plus n2 of h divided by 2 minus n2 of h. So 3 divided by this 3 will become 1, and n2 of h divided by 2 minus n2 of h divided by 3, this will survive. So far, I did calculation up to this term. Remember, this is equal to, this term divided by 3 is equal to n3 of h. This term divided by 1 is equal to n2 of h. And remember, I have replaced this n by n1. Let us go further. The target is to get of order h raised to the power 4. So let us get rid of this term. The previous which I reproduced, replace h by 2. When I replace h by 2, so this will become n3 of h divided by 2. This 1 over 8k 3h divided by 2 raised to the power 3h cube divided by 8, which you can see here. 7 divided by 32 k4 h divided by 2 raised to the power 4 is h raised to the power 4 divided by 16. As I told you that this is positive sign, and similarly this is positive. Let's get rid of this term. So you can see that the difference is, multiply equation number 6 by 8 and do the subtraction of equation number 5. So when you do that, this will become 8m minus m is equal to 7m. 8 in 3 h divided by 2 minus in 3 of h divided by 2, it's coming from there. If you multiply this by 8, so this 8 will cancel, and this term cancels with that term, plus multiply this with 8, so this will become h4 divided by 2. So 7 divided by 64, and 7 divided by 64 minus 7 divided by 32 gives you minus 7 divided by 32, and so on. I replace this term by n4 of h. This term divided by 7. This term divided by 7 I replace by n4 of h. So when you do the division by 7, so this will become 1 over 32 k4 h4. Remember, target is the approximation of m. but we are increasing the order of h, started from 1 and reach up to different values. This procedure will continue. I reach up to j steps. I approximated m by n j of h plus order of h raised to the power j, because you can see if this is 4, so this is h raised to the power 3 or 4. If this is 3, so this is h raised to the power 3. So if this becomes j, so this will become h raised to the power j. The formula has been written in this form. Look at this one. I reproduce the previous table up to this step. So I can write this was n4 of h. So I can write this is 7 n3 of h divided by 2 plus n3 of h divided by 2 minus n3 of h. So when I divide 7 by 7, I get in 1, and on the other two terms, they have been divided by 7. And this procedure continue. I have written nj of s plus order of h raised to the power j, and have shown that this is the value of nj of h. How? Look at this one. There is 1, 3, 7. So I can write 1 as 2 raised to the power 2 minus 1. I want to link this with this number. So 2 raised to the power 1 minus 1, 2 minus 1 is equal to 1. So you can see this one. Similarly, I've come to 3. So I can write 3 is equal to 2 raised to the power this 3 minus 1 minus 1. So this becomes 2 raised to the power 4, 2 raised to the power, 2 raised to the power 2, which is 4, 4 minus 1 is equal to 3. And similarly, if you look at this 7, I want to link this with this 4. So 2 raised to the power 4 minus 1 minus 1. So this is 2 raised to the power 3, which is 8. 8 minus 1 is. So you can see this is the generalization. If you're having 2, there is 1, it's 2 raised to the power 2. If you got n3, so 2 raised to the power 3 minus 1. If you're having 4, 2 raised to the power 4 minus 1. So if I have j, so there should be 2 raised to the power j minus 1 minus 1. That's the way if this is 2, so this is 1 everywhere. This is 3, so 2 is everywhere. If this is 4, so 3 is everywhere. So this is j, so j minus 1 is there. This is the general term for n. So basically, n was your formula. N was your formula using for, whether differentiation, integration, or something like that. So what will be the target in Richardson? We have to find out nj of h, and that will approximate. If we are going for derivative, so it will approximate the derivative. If you are going for integration, it will approximate the integration. If you are going for any other kind of Lagrange polynomial, something like that, so that will go accordingly. What is the order? Look at this one. As I told before, in case of n1 of h, the error was starting from h raised to the power 1. In this case, the error will be starting off order of h square. In this case, that will be of order h cube. In this case, that will be of order h raised to the power 4. As I told you before, so this is 4, so this is of order 4. If this is 3, so this is of order 3. So that's the reason I have written it over here. If someone asks you, use the Richardson extrapolation to get error of order h raised to the power 1. So you need to find out n1. If asking you find out of order h square, so you have to find out n2. Of order h3, so you have to find out n3. Of order h4, you have to find out n4. Of order h raised to the power 5, then you have to find out n5. But remember, I told you at the start that m is equal to n of h plus k1 h plus k2 h square plus k3 h cube. In other words, the power of h increases by 1. What you have to do, n2 of h is required because n1 is coming from the first stage. N2 of h is required. So if you substitute j is equal to 2, it means that you need n1 of h divided by 2. You need this value, and you need n1 of h. You need these two values. If these two values are known, then you can find out this value. So that will be the step. First find out n1 of h, then find out n1 of h divided by 2. So if you replace j by 2, so this will become n1 of h divided by 2, which you have computed here, n1 of h divided by 2, which you have computed here, and 1 of h, which you have computed there. So this will be the order. Find out first this one, then finally find out n2 of h. And this n2 of h will be your approximation of m with error of order h square. If your target is to find out error of order h raised to the power 3, then you need other values. How? When you substitute j is equal to 3, so you need n2 of h divided by 2. n2 of h divided by 2. n2 of h divided by 2. And n2 of h, which you have computed there. Why I need this term? Now let's come to this one. If the target is to find out n2 of h divided by 2, n2, substitute j is equal to 2. So this will become 1, this will become 1, this will become 1. But this time you have to replace h by 2. When you replace h by 2, you need h divided by 4, and 1 of h divided by 4, and 1 of h divided by 4. That's the reason you have to find out this value. And this will be n1 of h divided by 2, which you have computed in the previous step. Now you approximated m by n3 of h, but in this case error is of order h raised to the power 3. Now if your target is to find out error of h raised to the power 4, then what you have to do? You have to find out n4 of h. For n4 of h, j is equal to 4, you need n3 of h divided by 2. You need n3 of h. n3 of h you have computed in the previous step. n3 of h divided by 2 you have to find out. And when you are computing n3 of h, you need n2. Replace h by 2. So this will be n3 of h by 2 is equal to n2 of h divided by 4. n2 of h divided by 4. That's the reason we have to find out before this computation. And when you are going for n2 of h divided by 4, so replace j by 2 and h by 4. So this will become n2 of h by 4. This will become n1 of h divided by 8. That's the reason I have computed this value. And if you are going for error of order h raised to the power 5, so what you have to do? You have to find out n5 of h. For n5 of h you need, substitute j is equal to 5. You need n4 of h, which is there. You need n4 of h divided by 2. That's the reason I have computed it over here. That will give you, but for n4 of h divided by 2, you have to find out some value. Replace j by 4 and h by 2. So this will be n3 of h divided by 4. That's the reason I am computing n3 of h divided by 4 before this computation. And of course n3 of h by 2 is required, which we have computed in the previous step. To find out n3 of h divided by 4, replace j by 3 and h by 4, you need n2 of h divided by 8. n2 of h divided by 8. n2 of h divided by 4. n2 of h divided by 4 you have computed. n2 of h divided by 8 you have to find out. But for n2 of h divided by 2, when I replace j by 2 and h by 8, I need n1 of h divided by 16. That's the reason I'm saying n1 of h divided by 16 is required. So this is the order to find out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So for n5 of h you need these 14 calculations to find out n5 of h. And of course that will be your approximated value of m. Now let's go ahead. For example, your approximation is of this type. You can see the power of h is changing by 2 now. Previous case you saw that there was h, then h square, h cube, h4 and so on. But now if your formula is such that the error is changing in this order, the power of h is changing in this order. So it's changing by 2 if you look at it. Formulas are normally the mid formulas, they are of this type. Then you have to adopt the same procedure which we adopted as I discussed right now. Replace h by 2, eliminate h square, get an equation, then replace h by 2, eliminate h raised to the power 4 to get error of order h raised to the power 6, then replace h by 2, get rid of h raised to the power 6 and get error of order h raised to the power 8. So procedure is the same. I am not deriving that again, but I will say this case ng of h of order h raised to the power 2j. Why 2j? Because in this case you can see this is 2, this is 4, this is 6 and this is 8. So it means that power is even. What will be? If you follow the same procedure which I adopted right now, everything is the same except there was 2 and here there is 4. That is the only difference. But my suggestion will be the procedure I discussed. Follow that procedure and see that how you are getting this 4. Or this derivation is there in your book also about the 4. So in this case, and previously I told you that you are getting error of order h, then error of order h square, error of order h cube and so on. But this time you can see that the power is changing by 2. They are of even order. So what you will be doing? The same criteria as I told you before. n2 of h you need n1 of h divided by 2, n1 as I discussed in the previous slide. But remember this time, when you are computing n2, your error is of order h raised to the power 4. So if you are using the formula with 2, then n2 of h gives you error of order h square. But if you are using 4, this formula, so n2 gives you error of order h raised to the power 4. The construction of the table is in similar fashion. So I'm not discussing this again. But remember n3 of h, when you are using this formula, your error is of order h raised to the power 6. n4 of h, your error is of order h raised to the power 8. And n5 gives you error of order h raised to the power 10. Normally, remember this formula we are using when n of h is the midpoint formula. And you saw that 5-point midpoint formula you did, and similarly 3-point midpoint formula you did. So if you do that expansion, in that expansion the power of h is varying by 2. So if you are using the previous formula, mean that when there is 2, so n2 of h gives you error of order h square. But if you are using this formula, then n2 of h gives you error of order h raised to the power 4. n3 of h, if you are using the previous formula, n3 of h computation will give you error of order h raised to the power 3. But if you are using this formula, then this will give you error of order h raised to the power 6, and so on. So this was all about the Richardson, how Richardson adopted the procedure to approximate value of an unknown. Let us consider an example. The question is, apply a Richardson extrapolation to determine n4 of h, an approximation to a prime of x0. Means that the target is to find out the derivative of the function at x is equal to x0. You are given n4 of h, you have to find out. This is not restricted which formula you are using. Are you using the formula where 2 has been used or 4 has been used? There is no any restriction on it. But remember, normally when we are using the midpoint formulas, then we are using the formula where there is 4. And when we are using the endpoint formula, so normally we are using the first case where there is 2. Function is given to you, the value of x0 is given, and h is given to you. Find out a prime of x0 using the Richardson extrapolation. I'm using the formula which is the 3-point midpoint formula. It means that we have to use 4 in the construction of n of j. Yani the second formula which I showed to you. We are using the 3-point midpoint formula, and just I have replaced this x0 by 1.2. Why I didn't replace h by 0.4? Because you know that we need different values of h to find out n1. So that's the reason I am computing this value in general. Just replaced x by 1.2 plus 4 over here. The sign of 1.2 plus h, and this will be 1.2 h whole cube minus, replace x by 1.2 minus h. So when you replace it, this will become minus 1.2 plus h, which you can see over here, sign of 1.2 minus h, and similarly 1.2 minus h whole cube. So this is the value of n1 in terms of h. You know this was the formula, and you can see that you need n4 of h. For n4 you need n3 of h divided by 2, and for n3 of h divided by 2 you need to find out n2 of h divided by 4, or for n2 of h divided by 4 you need n1 of h divided by 8. Means that you have to find out n1 of h, n1 of h divided by 2, n1 of h divided by 4, and n1 of h divided by 8. Replace h is equal to 0.4. That will give you n1 of h. So replace h is equal to 0.4 in this expression and simplify it, you are getting this value. I told you we need n1 of h divided by 2 also. So h divided by 2, h is 0.4 divided by 2 is 0.2. So replace h by 0.2 in this expression. You are getting n1 of 0.2, which is equal to n1 of h divided by 2. That's the value. Similarly, n1 of h divided by 4, h is 0.4, h divided by 4 will be 0.1. So replace h by 0.1 in this expression. You are getting the value of n1 of h divided by 4. Similarly, n1 of h divided by 8, h is 0.4, 0.4 divided by 8 is equal to 0.05. So replace h by 0.05 in this expression. You will be getting n1 of 0.05, which is basically n1 of h divided by 8. If you look at this formula, n4, so I need n3 of h and n2 of h. So now let's go for n2 of h. This is the formula which I reproduced, and when I replace j by 2, so this will be 4 raised to the power 2 minus 1, which is 4. 4 minus 1 is 3. 4 minus 1 is 3. You can see 3 there. J is equal to 2 and 1 of h divided by 2, and 1 of h divided by 2 minus n1 of h, which you can see over there, divided by 3. And if you take the LCM, so 3 n1 of h divided by 2 plus n1 of h divided by 2 gives you 4 n1 of h divided by 2 minus n1 of h divided. So you know the values from the previous calculation. N1 of h, which was actually n1 of 0.4, and n1 of h divided by 2 was n1 of 0.2, which you computed in the previous step, and just substitute the value. Remember, now when the value of this j is greater than 1, we don't need to use the original function. We have to play with these calculations now. Replace h by 0.4, and you know these values. N1 of 0.2 is known, and 1 of 0.4 is known. When you substitute the value in this expression, you are getting n2 of h. N4 was required, so for N4 you need N3 of h. For N3 of h you need N2 of h divided by 2 also. So let's find out N2 of h divided by 2. N2 of h divided by 2, h was 0.4, 0.4 divided by 2 is 0.2. So what you have to do, replace h is equal to 0.2 in this expression. You will be getting N1 of 0.2 divided by 2 is N1 of 0.05, which you have computed before, and N1 of 0.2 you have computed before. Substitute the value over here, and you will be getting N2 of 0.2. N2 of h divided by 4 is also required, which was clear. N4 of h. For N4 of h you need N3 of h divided by 2, and for N3 of h divided by 2 you need N2 of h divided by 4. So that's the reason I am computing N2 of h divided by 4. H is 0.4. 0.4 divided by 4 is 0.1. Sorry, in this case 0.2, 0.4 divided by 2 is 0. That's okay. 0.4 divided by 4 is 0.1. Just replace h by 0.1. You need N1 of 0.1 divided by 2, which is 0.05. And 1 of 0.05 was N1 of h divided by 8, which you computed in the previous step. And N1 of h, N1 of 0.1, that we have computed also. Substitute the values over here, and you will be getting N2 of h divided by 4. Now let's come to N3. Substitute j is equal to 3. J is equal to 3 into N2 of h divided by 2 you need. N2 of h divided by 2 minus N2 of h divided by 4 raised to the power 3 minus 1, which is equal to 4 raised to the power 2. 16 minus 1 is 16 minus 1 is 15. You can see over here, and if you take the LCM, you are getting 16 into of h divided by 2 minus into of h, which is equal to 15. Now let's substitute the value. N3 of h. So N2 of h divided by 2 you have computed there. N2 of h. N2 of h divided by 2 is available. N2 of h is available. Substitute the values over here. And you are getting N3 of h. Similarly, let's find out N2 of h, N3 of h divided by 2. Why? Because N4 of h, we need N3 of h divided by 2. So when I substitute N3 of h divided by 2, so this will be, the value of h is 0.2. Substitute the value of h is equal to 0.2, so you need 0.2 divided by 2, which is 0.1, the value is available there, and N2 of 0.2 is available there. Substitute the value over here, and you are getting the value of N3 of h divided by 2. When j is equal to 4, when j is equal to 4, so this is 4 raised to the power 3, which is 64 minus 1 is 63, which you can see over here. 64 minus 1, so if you take the LCM, so this will become 63 plus 1 is 64. Now the values of N3 of h by 2 is there, N3 of h is there. Substitute the value and you are getting the value of N4 of h, which was required, and this is the approximated value of the function 8x naught. This is approximated value of the derivative of the function 8x naught. In other words, a prime of 1.2 using the Richardson extrapolation. Now let us consider another example. The following data give approximation to the integration from 0 to pi sine of x dx. Which formula has been used? We don't know. But these are the values given to us. N1 of h, N1 of h by 2, N1 of h by 4, N1 of h divided by 8 is given to you. Use this data. So of course when you are using this data, you have to find out N4 of h. But remember, it's given to you that this is a kind of approximation. So you can see that the power of h is changing by 2. So of course you have to use the formula where there is 4. This is the general formula which you already know. Let's find out. And 1 of 8 it's given to you, so you don't need to use any formula, whatever the kind of formula has been used for this integration, but these are the values have been obtained. It's given to you. Approximation is of this type, so find out N4. If I'm saying that approximation is k1h plus k2h square plus k3h cube, then remember you have to use 2 here, not 4, because that is the requirement of the Richardson extrapolation. And 2, when you replace j by 2, so you are getting 4 raised to the power 1, so this is 3, 3 minus 1, again in similar fashion, when you take the LCMs, you are getting 3 plus 1 is equal to 4 minus n1 of h. Now n1 of h divided by 2 is known, and 1 of h is known. Substitute the values, you are getting N2 of h. Remember, h is not given to us in this problem, but just these values are given to us, so we are going accordingly. Now let's find out For n4 of h, as you saw in the previous case, you need to find out n2 of h divided by 2 and n1 of n2 of h divided by 4. So for n2 of h divided by 2, replace h by 2. So you need n1 of h divided by 4 minus n1 of h divided by 2. n1 of h divided by 4 is there, n1 of h divided by 2 is there, and when you substitute the value, you are getting the value of n2 of h divided by 2. For n2 of h divided by 4, replace h by 4. So you need n1 of h divided by 8, which is there. You need n1 of h divided by 4, which is there. So substitute this value and that value. In this expression, you are getting the value of n2 of h divided by n2 of h divided by 4. Now let's come to the reproduce the formula. n3 of h. n3 of h replaces j by 3. So this will be 2 raised to the power 2 minus 1, which is 16 minus 1, which is equal to 15. And if you take the LCM, so 15 plus 1 is 16 n2 of h divided by 2 minus n2 of h. In the previous slide, you saw that n2 of h you have computed, n2 of h divided by 2 you computed. Just substitute the values and that will give you the value of n3 of h. Similarly, for n3 of h divided by 2, replace h by 2. So this will become h by 4, this will become h by 2. And already you have these two values available. You have computed n2 of h divided by 4, you have computed n2 of h divided by 2. When you substitute the values, then you are getting the value of n3 of h divided by 2. Now let's come to the last value. This will be n3 of h divided by 2, which is there. n3 of h divided by 2, n3 of h, which is there. So just substitute the values, and the value of j is equal to 4. 4 minus 1 is 3. 4 raised to the power 3 is 64 minus 1 is 63. And if you take the LCM, so this will be 63 plus 1 is 64 minus n3 of h. n3 of h you have computed here, and n3 of h divided by 2 you have computed there. And when you substitute these values, you got the value of n4 of h, which is given by this quantity. And that is the approximated value of the integration which you had at the beginning. So you saw in these examples, in the first case, we computed derivative of the function at a particular point using the Richardson extrapolation. And in this example, you computed the integration of a function. Some informations were given because the numerical integration you will be doing after the differentiation. So they give you just the values. There are different formulas, which formula you are going to use. Now, for example, it's not given to you. You are given some tolerance. In this case, the question can also be asked, find out the approximated value of the integration when the error is of order h raised to the power 8 in this case. When you compute this value, so the error will be of order h raised to the power 6 and so on. So you saw that with the help of the Richardson extrapolation you are getting, and Richardson claims that we are getting better accuracy as compared to the normal technique. So this is the way how the Richardson extrapolation is working. Thank you very much.